Okay, so Chapter 5 review. As we talked about, this is going to be a bigger part of the midterm because there's no Chapter 5 test. So if you're comfortable with these questions, you should be A-okay for that section of the midterm. So if f is continuous and on a closed interval, meaning that it contains the endpoints, then f has both a maximum and a minimum. Oh my gosh, the struggle. Value on the interval. So we talked about the difference between absolute versus local. So an absolute minimum is the lowest possible. A local is just based on where the other points around it are. So out of all the points in this area, this one's the minimum, but it's not the lowest of the entire graph. Okay. So these two would be our absolute, and then these ones are all local. Okay. Remember, to find a local extreme value, we're going to take the derivative and set it equal to 0. Okay. A point where the derivative is going to equal 0 or the derivative doesn't exist. So remember the line, the 0 with the line through it. Well, you can't see anything I just did. So remember that 0 with the line through it means does not exist. Okay, so this point, because it's a cusp, that's a point where the derivative doesn't exist, but it is an absolute maximum in this case. Okay, so this is so shadowy. The mean value theorem. If a secant line is drawn on a function that is differentiable, there will be a point on that interval where the slope of the secant that you draw matches the slope of the tangent at a point between those two spots. So if we have something like a parabola like that, if we draw a secant between those two lines, we're going to have a point in between them where that line is parallel to that secant line. Okay, so example, if f of x is equal to cos x, then the mean value theorem guarantees that somewhere between 0 and pi over 3, f prime of x is going to equal the slope of the secant. So in this case, it doesn't actually ask you what f is or x is, it just wants you to figure out what it's going to be equal to. So to find that, we're going to say the secant slope is m is equal to, so we're doing y2 minus y1. So y2, we're plugging it in here. So cos pi over 3, it's going to be our y2 minus y1 cos of 0 over x2 minus x1. So cos pi over 3, if we think back to math 30, is 1/2. And then cos of 0 is 1. And then pi over 3 minus 0 is obviously pi over 3. So then we've got 1/2 minus 1, so it's going to be negative 1/2. And then times the reciprocal of this, so 3 over pi. So we get negative 3 over 2 pi. Okay. So basically what this means is somewhere between 0 and pi over 3, the derivative, which we know is the slope of the tangent, will be equal to negative 3 over 2 pi. So we could figure that out what that is by setting negative 3 over 2 pi equal to the derivative of cos x. Okay. Our third topic, was 5.3, so connecting f prime and f double prime with the graph of f. So if I gave you a graph of a derivative, could you tell me where the original one was increasing or decreasing, right? Like if I had a graph, if I said this was f prime at x, because it's positive all of here, that would tell you that between those two values, it would be increasing on the regular graph, right? All of the zeros on the f prime would be maxes or minimums on the original, right? We can figure out where the inflection points are, right? Because if we do the derivative of this one, we'd get f double prime. Those inflection points would be there, right? So there's lots that we can know about different graphs. So we can use a first derivative to test to determine the local extrema. So if we take the first derivative and set it equal to 0, that'll give us maxes and mins. When the first derivative is positive, the graph is increasing. When the first derivative is negative, the graph is decreasing. So that's when you'd want to set up your little chart and say, okay, here's the point that I found that's either a max or a min. Is it increasing or decreasing on either side? Because that'll actually tell you without drawing the graph whether that is a max or a min. If it goes from increasing to decreasing, we know it's a max. If it goes from decreasing to increasing, we know it's a min. Okay, and obviously that would look more like something that is differentiable, but hopefully you get the point. We can use a second derivative test to find the inflection points. So the graph will be concave up when the second derivative is positive and concave down when the second derivative is negative. So we're going to determine the x-coordinate of the point of inflection and the intervals of concavity for this graph. Okay, so if we're just looking for a point of inflection and the intervals of concavity, we don't have to worry about any of the first derivative stuff. So we're going to go straight to the second derivative, but obviously we need to do the first one to get there. So I'm going to write it as y prime. So the 3 is going to come down 12x squared plus 42x plus 36. And then y double prime is going to be 24x plus 42. So we set this thing equal to 0. We solve for x, so 24x, one of them is going to become negative. Divide both sides by 24. And then this is going to reduce to negative 7 over 4. They both divide by 6. Okay, so there is our inflection point. Now it doesn't actually ask for in this question the y coordinate, just says determine the x coordinate, so we've done that. And then the intervals of concavity, we want to know where is concave up and where is concave down, so that's where we're going to make our little chart. So x is either less than negative 7 over 4 or x is greater than negative 7 over 4. And I gave myself enough room this time to actually show you plugging in a value, but I know you guys know how to do that. So I'm going to say we're going to use negative 2 and we're going to use 0 because those are pretty easy numbers. So we're plugging this into y double prime, right? Because we want to know if the second derivative is positive or negative. So y double prime is going to be 24 times negative 2 plus 42. It's negative 48 plus 42. It's negative 6. So it's negative. It's negative. And so that means it is concave down. Over here, y double prime, I chose 0 because it's the easiest number to plug into things. So it's just 42, so it's positive, meaning that it's concave up. Okay, our next topic was modeling. So remember to read the problem carefully to really understand what the question's asking for. You will need to figure out your optimization, so which one you actually want to get the derivative of equation, as well as any constraint equations. So remember that the reason why we have constraint equations is we want only one variable, right? So we don't want area equals base times height. We want area is equal to just a function of b or h or whatever it is. So the one on the midterm, I think is fair, definitely. It's an area problem, but it's a little bit different than what you guys have seen before. My advice is to draw it and think through what it's gonna look like, okay? So that is my advice for the midterm one. But it's not like something crazy like the one on the assignment that we were talking about the other day. So it's an area one. It's a little bit different than what you guys have seen just because gotta mix it up somehow. But draw it and you should be all good. As an example, we're going to do an open top box is going to be made by cutting congruent squares. Congruent, remember, means the same of side length x from the corners of a 20 by 25 inch sheet. So if here is my sheet, this would be 20, this would be 25. We're going to cut the corners. It's not a very good rectangle, but whatever, of side length x. So if we cut all those out, and these are squares, so x and x. If we cut all these out, this is going to be the actual dimension of the box. Okay, so this is going to be 25 minus 2x, because you're getting an x off each side. This is going to be 20 minus 2x. So the volume of this thing is going to be 25 minus 2x times 20 minus 2x times the height, which is going to be the x that actually like folds up. Okay, so this is the thing that we want to optimize. This one's nice because it's already just in terms of one variable. We talked about how it's easiest if we distribute this out instead of trying to do product rule. So 25 times 20 is 500. Minus 40x minus 50x plus 4x squared. That whole thing gets multiplied by an x. I'm going to flip the into descending degree. So 4x cubed. This combines to 90x squared and then plus 500x. So that's our equation that we want to do the derivative of. So v prime at x is going to be 12x squared minus 180x plus 500. Okay, and then we want to set that thing equal to 0. Now, if you didn't have your graphing calculators, you would have to quadratic equation this. You could factor out like a 4, and then try and factor it. It doesn't factor. But since you do have your calculators, what we're going to do is we're going to graph it and find the x-intercepts. So if we just plug this thing in, so 12x squared minus 180x plus 500, graph it. Notice how I've got like nothing helpful here, but that is going to be one of my solutions. Okay, if I zoom, fit this, hopefully it does something nice. It doesn't really do anything nice. That's okay, whatever. So we're looking for that intercept there. So we're gonna go 0. Remember that this is not the actual equation. Oops, I messed that up. This is not the actual equation of the volume. It's the derivative of the volume. So, why is this not working? Left bound. There, right bound. There, guess. There we go. So we get x is equal to 3.68. Okay, so that would be within the domain, right? Because our domain, it can't get, there's going to be another intercept. If we think about this as a parabola, there's going to be another intercept over here somewhere, but that's going to be outside of our acceptable domain. Because if we choose x is bigger than 10, which is our scale on our x-axis here, this is 10. If we choose an x value that's bigger than that, this side length isn't going to exist because we're going to take 20, subtract like 22. That doesn't make any sense, right? So there is our x, and we can look back at the question and know that we're talking about inches. The other thing that it says is what is that maximum value? So V max, we're going to plug that 3.68 back into whichever equation you want. I'm going to go to the top one because I think it's the easiest to not make mistakes. If you've actually done it on your calculator, it saves that value of x, which is nice. So you can get out of there, and then you can go 25 minus 2 times x, and it's going to use that x value that it's remembering. So then minus 2x and then times x, hit enter. So it's going to be 820.5, and this is going to be inches cubed because it's a volume. And then the last section, there will be a question on related rates because I haven't quizzed you or tested you at all on it. So a hot air balloon is rising straight up from a level field, and it's being tracked by a rangefinder that's 500 feet from the liftoff point. So if we think about this, we've got 500 feet across the bottom. So if my balloon picked up from here and went straight up, my hot air balloon is going to be so pretty. Somewhere up there. Looks like a basketball. Okay, so the rangefinder is over here. So at the moment, the rangefinder's elevation angle is pi over 4. So that means this is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. So that means d theta dt is equal to 0.14. So that angle is growing. And that would be radians per minute. So then we want to know how fast the balloon, so how y is changing with respect to time, is going at that moment, okay? The other thing that we know, because our x isn't changing, because that 500 meters isn't changing, we know dx dt is going to be equal to 0, okay? So we need to figure out an equation that relates all of this thing. So you've got an angle, an opposite side, and adjacent side. So I know that tan is going to relate those things. So tan equals opposite over adjacent. So we can replace that with y over x. Because this side length here is just y. So if I want to do the derivative of this and implicitly differentiate it, I know I want dy dt, so I want that by itself is one thing. And doing a quotient rule is harder than multiplying both sides by x and doing a product rule. So I'm going to actually rearrange this thing to go x tan theta and do the derivative like this because I think that's easier. So then we're doing the derivative, remember, implicitly on both sides with respect to time. So it's going to be dy dt, and then we're going to have a product rule. So it's going to be the first one times the derivative of the second one. So derivative of the second one is secant squared of theta, and then you have to multiply by the derivative of that inside thing. And this I just got off my formula sheet. So it's going to be d theta dt. So how theta is changing with respect to time, plus the derivative of the second one, so dx dt times tan theta. Okay, and then we're just plugging in numbers. So x is 500 feet. Remember, this guy is our x. Secant squared of pi over 4, and that's going to be radians. And then d theta dt is 0.14 radians per minute. Okay, so radians generally cancel out, right? We don't actually usually write radians in our calculations, which is nice because now we have feet per minute. This is not second, right? This is secant, so feet per minute, which makes sense because that's going to be a velocity, which is changing here. And then plus dx dt is 0. So we don't even care what tan theta is. So when we plug all of this in, we're going to get 140 feet per minute. So dy dt, how y is changing with respect to time, is 140 feet per minute. It's positive because if the angle is getting bigger, the balloon is going up. Okay, so there's chapter 5 review. If you're comfortable with all of that, you should feel a-okay about the chapter 5 stuff that is on the midterm.